Thank you. So today's talk is the last lecture. We're talking about Arakelov geometry. Of an adelic curve. So in the lecture we fix an adelic curve. So S is K. So K is a field, and we have some measure space omega A nu, and the phi from omega to the set of all absolute values of K. So which is proper. So with K countable. So of course, so it suffices to assume that K admits a countable subfield, which is dense in every completion. So, but for simplicity, we just assume that K is countable. So now I will talk about higher dimensional geometry. So in previous talks we were talking about some geometry of adelic curve, but now we consider some variety. So the most fundamental object is adelic line bundle. So here I just talk about a line bundle. You may ask that in general case we may possibly think about a general vector bundle. But in some sense, you can take the projective space of the general vector bundle, and then you have a tautological line bundle on it, and then you can naturally equip it with some matrix to reduce the problem to line bundle case. So line bundle case is really fundamental. So now we fix some integral scheme, projective scheme. Which I denoted by pi for x2 spec k. And for each omega, let x omega be the fiber product of x with spec of completion over spec k. So there you obtain some scheme of the field, complete the field spec k omega. Then the point is that we need to attach some analytic objects in order to complete, in some sense, the algebraic data. So that is very important. So x omega analytic. So there is a new space. So this is just a set of pairs. So x, which is written as p, and an absolute value. So here p is a scheme point of x omega, and this one is an absolute value. On kappa x, which is just defined as kappa of p. So this is just a residue field of the scheme x omega at the scheme point p. So then you have a natural map for x omega 1 to x omega. For this set to the scheme, just you send x to the scheme point p, to the first coordinate. That gives you a map. And if U in x omega is a Zariski open subset, and if you have some regular function on U. Then you get something like absolute value of f, which is defined on j minus 1 of U, and takes value in positive real, a set of positive real numbers. So how to define this function? So if you evaluate this function at some point x, so you just take so the residue class of f in the residue field of x, and then it will give you some element in kappa of x in the residue field, and then you have some absolute value on the residue field, so you can evaluate at x. So you take the absolute value of this element in the residue field with respect to this absolute value. So note that for each scheme point, you may have several absolute values. So it gives you several different points in this set of analytic space. And of course, I need to introduce some topology on such a set of pairs. So this is called the Berkovich topology. It is just the most coarse topology, so making the map J and all functions so the value continuous. That means for each Zariski open subset U, J minus 1 U is an open set in the analytic space, and also all such functions are continuous with respect to the Berkovich topology. So of course, if you take a very fine topology, then everything becomes continuous. You take the most coarse topology, making what you need to compute continuous. Now I can give you a formal definition for metrized line bundle. So let L be an invertible module. So for any omega, so let L omega be the pullback of L or x omega. So x omega is a fiber product, so you have a projection to x, you can pull back L to x omega. And then by metric family, so maybe before talking about metric family, by continuous metric, or L omega, we mean a collection phi omega, which is given by a by a collection with parameter in x omega n. So for each point of x omega n, you fix a norm, so of norms. So note that I just used one line bar to denote this norm. So the reason is that such thing is a norm on L. So tensor Ox kappa hat of X. So this is a completion of kappa X with respect to the absolute value at X. So this is just one line. So one-dimensional vector space of a kappa hat of X. So sometimes it's to distinguish with other norms, I just use one line bar to denote this norm. So of course I need some condition to denote the continuous property. So such that for any u in x omega, there is Q open, and any section S mu gamma of u L omega. So the function S of phi omega, which goes from j minus 1 of u to positive. So this is a function I vary the variable x. I need that this function to be continuous. Of course, with respect to the Bldg topology that I have fully introduced here. And so we call metric family so now this is a family parametrized by omega. So where phi omega is a continuous metric or L omega. So here in the definition of Bldg topology, so each absolute value of regular function is continuous. So namely, to verify the continuity of a metric, it suffices to take find the cover of scheme x omega, and on each component you pick some generator of the invertible line bundle, and you consider the norm of the generator. So if all such functions are continuous, then the metric is automatically continuous because in each affine cover. So if you take some general section, it's written by a regular function times the generator. So it's automatically continuous. Okay, so I will give you some examples. So let E be a finite dimensional vector space. And Xi be a non-family. Then you fix some surjective homomorphism of vector bundles. So So if you have such data, you find that for any omega and any x in x omega adelic, the beta will induces something like beta x. So from E times k kappa x to L times OX, so kappa hat x. So you have just a surjective linear map, and then so we can consider something like psi beta and omega. So here from x, so you consider such norm be the quotient norm. So induced by this map. So of course you have some norm which is here. So you need to extend the norm on this space. You have a norm on E k omega. You need to extend this norm to this space. I will not give the detail because the extension is not unique, but you need to fix some extension. So usually, so I will give you some properties which characterize the extension. So this one and by beta x. So instead of giving the definition of the extension, I will just give you a formula which defines this norm. So find the L in L tensor OX kappa hat of x. So by definition, so the norm of L at x is given by the infimum of S in E, and the lambda in kappa hat of x, such that the beta s x of s is lambda L. So you consider all the sections S in E, and you evaluate beta x of x, so it's always given by lambda times something, lambda times some lambda times L, and then you take lambda omega minus 1 times norm of S omega. So it gives the definition for this metric. Then you have some metric family. So you take phi psi beta omega, which is this collection. So this is called the quotient metric. Induced by the norm at omega and beta. And then you have a family of norms, so phi of psi beta, which is the correction of a phi psi beta omega or omega in omega, is a norm family. It's a metric family, sorry. So it's called the quotient metric family. So induced by psi and beta. So this is the first example, and also the fundamental example in the study of metrized line bundles. And there are some other natural constructions. So for example, if you have L1 and L2, which are invertible X modules, and phi 1 and phi 2 be a metric families. On L1 and L2. So then you can define some tensor product. So here I just write in the addition form. So this is a metric family. On the tensor product of L1 and L2. So just it's given by if you evaluate L1 tensor L2. So these are sections of L1, L2 on some Bldg open subsets. So you have phi 1 plus phi 2 omega, and at some point x is just given by L1 phi 1 omega x times L2 phi 2 omega x. So this is a tensor product metric family. So it's very easy to see that if phi 1 and phi 2 are continuous, the tensor product is also continuous, so you automatically get a continuous metric family. And also we can consider some dual metric family. So given L and phi metric family, so we will get some L dual and minus phi as follows. So for any omega in omega, x in x omega n, L in L tensor OX that by x hat, and alpha in L dual tensor x by x hat. So alpha is a dual element in the dual space. So therefore you can evaluate alpha at L. So this will produce you some local regular function. So you can consider its absolute value at x. So this is given by the norm of L of x times the norm of alpha minus phi omega x. So this formula will give you the definition of the metric family minus phi. And also you can consider the pullback of metric family. So we consider f from y to x with some projective K-morphism. So given L and phi on x, so we will define a new metric family. So you have f star of L and some f star of phi as follows. So for any omega in omega, so y in y omega n, and also x is f omega n of y. So maybe I need to say a little bit. So phi y is given by some y, some q, and some absolute value of y. And then this x is given by just f omega of q. So this is an element, scheme point, which is the image of the scheme point q. And then if you consider the residue field of this scheme point, so you find that it admits an extension which is a residue field of q, because you have a morphism of schemes. So you can consider the restriction of this absolute value, which is defined on a larger field, to the residue field. So here you just take a restriction of this absolute value. So that will produce you a point in the vector space. So it's just defined as the image of f omega n. Okay, so so if you take some L in f of up star of L tensor Oy of kappa y, so L can be written as some L0 tensor lambda. Here lambda is in kappa y, and L0 is in L tensor Ox kappa hat of x. So just the extension is just given by such thing. So then the metric can be computed as follows. So the norm of L at f up star phi omega at y. So it's given by L0 of phi omega at x times the absolute value of lambda at y. So this gives you the definition of this metric. So that is pullback. And also you can consider the degenerate case. So if x is just given by spectral k prime, where k prime over k is an algebraic extension, then phi, so L phi, so it's given as an invertible module of x plus continuous metric family. It's just can be considered as so a finite dimensional k vector space, k prime vector space, plus a norm family or L. So with respect to the adelic curve, which is given by k prime and omega prime, maybe omega k prime, sorry, and a k prime, neo k prime, and phi k prime. So here, although you consider some general geometry, but if x is of relative dimension 0 over k, so maybe algebraic extension is not so good. Maybe finite extension is better, because I assume the morphism to be projective. Yeah. So here you have some geometric object which was of relative dimension 0. Then it could be considered as some cover of adelic curve, and the data of a metric family is compatible to the data of a norm family that you have learned in previous lectures. So it shows that this new geometry is compatible with the geometry that you have seen before. And finally, I will give you a notion. So let L be some invertible OX module. And if you have two metric family, on the same line bundle for any omega, so we let local distance of phi 1 and phi 2 at omega as the supraman for x in x omega 1. So like of phi 1 omega x over phi 2 omega of x. So I can write this because these are two norms on the same one-dimensional vector space. So they just differ by some positive number. So you can compute the for all points comparison of two metrics. So this is always finite, because these two metrics are continuous, and I didn't say, but it is true that x omega n is a compact topological space. So provided that x is proper over k, so that is the case because x is assumed to be projective, and so this number is always finite. Okay. So now you have the definition of metric families, and also several examples and constructions. So maybe the examples are still abstract, but you can use them to produce many reasonable metric families. So as in the one-dimensional case for adelic curves, so you cannot deal with arbitrary metric families because it will not produce interesting arithmetic invariants. So you still need some properties like measurability or dominancy in order to get reasonable arithmetic objects. So it's now what we will consider. So I will give you the definition. So we consider a pair L and phi such that L is very ample. So in this case, you can realize L as some quotient. So I just erase it. So you can realize L just as a quotient of some vector space over K. So in this case, we say that L is dominated. So if there exists adelic vector bundle E xi on S, and the surjective OX linear homomorphism beta from pi upper star of E to L. So such that which defines close the embedding from X to a projective space of E. And such that the upper integral on omega local distance of phi and the phi psi beta. So this is the quotient metric family that I have just erased. So I require that the upper integral of the distance between phi and phi psi beta is finite. So this is the requirement for the dominancy. So in some sense, so if the dominancy is satisfied, then you can define some finite arithmetic invariants. So how to deal with the general case? So in general, so if we can write L as some L1 tensor L2 dual, and the phi is phi 1 minus phi 2. So I should have written phi 1 plus minus phi 2, you can understand. So you have some metric family here, you compute the tensor product with the dual. So with L1 and L2 very ample, and phi 1 and phi 2 dominated. In this case, we just say that L phi is dominated. So you see, it is very similar to a geometric case. So if you want to prove, so you want to check some nice property, you just assume your line bundle to be very ample, and then you write there's a difference of two very ample line bundles. Of course, we need to consider metric family here, but treatment is quite similar. So there remains some trouble. So in the case where L is very ample, you need to check that these two definitions give you the same property. So I leave you as an exercise. So in the sense that if you have a very ample line bundle, which is written as a difference of two very ample line bundles, then you need to prove that maybe the weaker condition will be the equivalent to the initial definition. So in some sense, dominated one are given by some quotient metric, or difference of quotient metrics. Okay, so just a little remark. So we consider a case where L is given by a trivial line bundle. So then metric family, so maybe phi corresponds to a family like a log of the unit section. So you have this family for omega in omega. So this one is just a continuous function. Or x omega n. So given a metric family is the same thing to take a family of continuous functions. And then phi is dominated is equivalent to the integral, upper integral of omega. So the sup of x in x omega n, the absolute value of this function so with respect to nu d omega is finite. So you take the superman of this function, so this produces you something with finite upper integral. Okay. So now this is dominancy, and also we need the condition of measurability. So we, as before, we consider L phi. So we say that phi is measurable if in the first case for any closed point P of x, so P ab star of phi is a measurable norm family or P ab star of L. So here so you take the residue field of P, it is a finite extension of the base field. So maybe as I said before, so if you have a finite extension given some line bundle and the metric family is the same thing to consider a vector finite dimension, so one-dimensional vector space plus a norm family. So I can require this norm family to be measurable. And what is a little bit complicated is for any x in xn. So here consider the trivial valuation. Okay, so this is automatically computed, so you can consider such a backward space. So for any L in L tensor OX kappa x hat, I require that the function omega in omega 0 goes to L phi omega of x. So is A restricted or omega 0 measurable. So here omega 0 is given by the set of omega such that the absolute value indexed by omega is trivial. So for the trivial valuation case, it's not enough to consider the measurability at closed point. You need to consider some measurability of So also one-dimensional point. So here I just give some stronger condition, but.
And the second one, so for all and accumulating element of x, and it should be x omega.
Here the point is that you have several copies of the same analytic space, so you can fix one point in the analytic space and consider it as several copies in different omega. So if you like, you can write x omega, but it's just the same point.
Yeah.
And consider
but in the notation, so for the second condition, and then I mean the two circle.
Yeah.
X is element of x. X is
yeah.
Just here. Okay. Yeah. Again.
So I take the triple relation okay, and then I can construct some x and so without considering any omega. And then for each omega such that this is triple, so I can identify x and to x omega, and then I can evaluate it at x. And there are several copies. There could be several copies. Okay. So now. So finally we say that L5 is an adelic line bundle. If phi is dominated and measurable, so the most important thing is that now we have some good objects, and then we can define some arithmetic invariants. So the most important invariant is the height function. So it's a fundamental construction for Diophantine problems. So you need a height function to measure the complexity of closed points, complexity of closed subvarieties, and etc. So I just give the definition. So let L5 be an adelic line bundle. So for any closed point, P of x, so that's H of L5 P be the Arakelov degree of P upper star of L and the P up star of phi. So so you can check that this dominated and measurable metric non-family, and so that it's adelic vector bundle on some finite cover of S. You can evaluate Arakelov degree. So you have some properties that I will not give the proof, but it's not complicated. So the height of L1 tends L2, and the phi1 plus phi2. So it's so as a function. So this is given by height of L1 phi1 and plus height of L2 phi2. So this is a very good property because if you take the point of view of very height machine, so this is an equality but up to some bounded function. Sometimes it's not so convenient. And then if you have also h of L phi as a function is minus h of L duo minus phi. So also so h of if you would consider two copies of metric family on the same line bundle, so h of L phi 1 p minus h of L phi 2 p. So this is bounded by the integral of omega, the distance of phi 1 by 2, and the nu d omega. So here I write the integral because assuming the measurability of phi 1 and phi 2, you can check that d omega is also measurable. So in particular, this is finite. So if you assume phi 1 and phi 2 to be dominated and measurable. And so unfortunately, the Northcott property is not always true for general adelic curve, so you cannot always say finiteness of the solution of some Diophant type problems with bounded height. So, so assume that S has Northcott property. Namely, so you can consider a set of A in K such that the integral of omega log of max of the absolute value A and the 1 mu d omega smaller than C is finite. For any C positive. And then, as in the classical number field case, for any C positive, for any delta positive, so the set P Ex of K, so this is absolute algebraic closure. Okay, so I consider our closed points such that the height is bounded by is bounded by C, and the degree of the point is bounded by delta. So this is a finite, provided that L is ample. So if L is ample, so this height function will also have the Northcott property if S has the Northcott property. So of course this condition should be checked for different situations. Okay, now so this is the height invariance of the adelic line bundle. So you can define other things that I will not introduce today. So then in Diophant type problems, it is very important to also consider the global invariance. So height invariance is in some sense local, and you need to consider the linear series, and it will produce you some global invariance. So in general, you need to combine local and global invariants to prove some Dufang type properties. So I will give you, so it's a new section. So I will give the statement of the theorem. So that phi be an adelic line bundle on X. So for any omega in omega, will that the norm of phi omega is the norm on this vector space H0 of X omega L omega. So you identify this as H0 of X L. Tensor K omega as follows. So for any S in this space, the norm of S at phi omega is just the sup norm. So it's given by the sup of X in X omega n. So you can evaluate S at X to produce you some local section. Then you can compute its norm. The conclusion is that H0 of XL equipped with this norm family of phi omega, for omega in omega. So this one is an adelic vector bundle. On the base adelic curve. So we will denote it by pi lower star of L phi in the following. So consequence is that we can consider family like pi lower star of L to power n and n phi, and then you let n vary in the set of natural numbers. So this is the rhythmic counterpart. Of the graded linear series Dirac sum H0 of X L to power n. So I have no time to give the proof for this theorem. Just I can mention that, for example, if you want to prove the measurability, so for example, you can use, for example, the fact that if omega, this absolute value is not trivial, then the set of closure points is dense in the adelic space. So you can use this fact. And on each closure point, you have some function which is measurable, and you take the superman of all these functions. It's also measurable because the set of closure points is countable. Remember that in the beginning I've assumed the field K to be countable, and therefore the set of closure points is also countable. So in some sense, the countability is important in the theory because we need to so keep everything measurable. So maybe if you want to treat with uncountable field, then maybe it is better to not introduce the measure space, but rather some topological space. And you need to pay attention to ensure every convergence to be uniform, and then you remain in a category of continuous functions. I think it is also possible to treat some problem if you don't assume the countability of the field. Okay. Now you have already seen this previous talk some invariants like volume function. So we can do the same thing for the adelic line bundle case. So let D be the dimension of X. So if L and phi is an adelic line bundle, with that, firstly the geometric volume of L. So this does not depend on the on phi. So it's just the limit sup of n goes to infinity. Then you compute the dimension over k of h0 x L to power n and divided by n to power d over d factorial. So we say that L is big if this volume is positive. The arithmetic counterpart, so is given as follows. So volume hat of L phi is given by a limit sup where n goes to the infinity. So here we take a positive degree. So I have explained to you why positive degrees should be considered. So in the case of a function field, it is very similar to H0. So, but in a adelic curve case, you cannot consider really a set of lattice points in the unit more. So you need to take a degree hat. So a fundamental observation is that here you have n to power d over d factorial, and here you have n to power d plus 1 over d plus 1 factorial. The reason is that even if your variety is defined over k, but if you consider k as an adelic curve, it's really a curve, and then your relative d-dimensional variety should have a total dimension d plus 1. So that is the reason why we call as an adelic curve, because relative geometry over a curve has dimension d plus 1. If the relative dimension is d, the total dimension is d plus 1. So that is the reason why this is called an adelic curve. So if this volume function is positive, we say that alpha is big. So of course, if you compare with algebraic geometry, it is much more natural to introduce intersection theory in the beginning and say that so such invariant should be given by the intersection number if alpha is very kind. And then the next step is to introduce a volume function for general not so kind objects. But the problem here is that technically we are not yet able to define the intersection number. So that will be done, I think. But for the moment, no. We don't know how to define the intersection theory. But fortunately, for volume function, it is possible because of the combinatorial argument that I have described a little bit during the previous talk. So now I will tell you how to make such a combinatorial argument. So this argument is called the Newton or Kongoff bodies. So I will give you firstly the definition. So we equip the additive group z2 power d with a lexicographic order. So recall that it is given by maybe A1 AD is smaller or equal to B1 to BD if and only if there exists some J, and in 1 to D such that AI is equal to a BI if I is 1 is equal to J, and also AI is strictly smaller than BI if I is equal to J plus 1. So of course if J is D, then this condition cannot be checked because then I is not well defined as an index, and then you have equality of two vectors. So what is the property of this? So this is a total order. In the sense that you can compare any pair of vectors. And also for any alpha being n2 power d, you always have 0 smaller than alpha. So this 0 is the 0 vector. This is smaller than alpha. And also, so alpha smaller than beta implies that for any gamma in z power d, you have alpha plus gamma. smaller than beta plus gamma. So these are very nice properties of this this order. So then we also fix the variety that you have seen before. So we call admissible evaluation on the function field kx. So any map V for kx to z power d union infinity, such that so this is a valuation. So you have some axioms of valuations. So for example, V of f is infinity if and only if f is 0. And also if you take a V of f times g, so this is given by V of f plus V of g. So this is just the very classical properties. So V of f plus g so this is bounded from below by mean of Vf and Vg. And finally, what is important is that for any alpha, if we let kx strictly of bigger than alpha, so this is just a set of f in kx such that so I didn't so there's one other condition is that v of f is 0 if f is inside k which is not 0. So this is one of condition that I forgot. So f in kx is such that okay, v of f is bigger than alpha. So of course we can define k of x strictly bigger than alpha, which is the same thing. And this condition together with this condition will imply that these two sets are actually vector spaces over K, over this base field K. And the fourth condition requires that the dimension over K of Kx greater or equal to alpha divided by Kx strictly greater than alpha is either 0 or 1. So this quotient vector space should have a dimension either 0 or 1. So so how to get such valuation? I will just give you some example. So take some regular points. So we need to assume that regular points exist. Some p in xk assumed to be regular. Then what you get is that so the local ring is a regular local ring. So OXP is a regular local K K algebra of dimension D. So of course, you cannot say much more because you have so many regular local ring. But if you take O XP, you take the completion, then by Cohen, by a theorem of Cohen, this will be isomorphic to such formal series ring. So maybe a T1 to TD. So here T1 and TD is a regular sequence of this regular local ring. And then so any F is this regular local ring can be written as some A which is not 0 times T to power some alpha plus some beta strictly greater than alpha of K T to power beta. So you have the development of your so formal series such like that, and then you take a V of F to be the first term, which is alpha here, and then you get some valuation on this ring, which verifies several properties, and then you can pass to the fraction field of this ring. So the fraction field of this ring will contain the fraction field so of this regular local ring, which is the field of rational functions. So then you get some valuation on the field of rational functions which satisfy all these properties. So that is one example. So of course, if you take such quotient, we just find the dimension to be 1 for this larger field. So for the smaller field, you have the dimension will be 0 or 1, so smaller or equal to 1. Okay, so why this fourth condition is very important? So what's the interesting thing is that so if E is K vector subspace of Kx, then what you can see is that the number of V, maybe V of E of non-zero vectors in E is just the dimension of E over K. So the reason is that you can decompose E into some sequence of decreasing sequence according to their valuation, and for each term, for each consecutive terms in this decreasing sequence, a quotient space will have a dimension 0 or 1. And then if you take the sum of all these terms, it will reproduce you the dimension of E. So that is very interesting. So we can use such combinatorial objects to reproduce the dimension of E. So that's the main idea. Okay. So now let EL be an invertible OX module now we fix some trivialization of L or Zariski open subset. And then we can consider some k-linear map. So gamma of x and 2 power n, it's sent to x of u. And this is sent to k of x as follows. So if you have some global section here, so you can consider the restriction of s or u divided by s. So maybe I need to write s0 to power n. And then this produces you some regular function, so which is subset of a rational function. So like this, you can consider this thing as a vector subspace of kx. So and then you can consider a variation. So of course the variation will depend on several things. So it will depend on the choice of v. It depends also on the choice of the local trivialization. Okay. Now, if E is a graded sub K algebra, of this sum, so we define the Newton concave body of E as so it's denoted by delta of E. It's by definition a convex Hall of the set alpha over n with alpha in V of En with 0 excluded. So now the theorem may be due to adelic and Kowalski. And also Lassensfeld. Mistata. Is to say that integral on delta of E 1 of dx is given by the limit sub of n goes to the infinity dimension k of En over n to power d. So the idea of proof is that if you count this cardinal, you just recover dimension k of En. So of course you have some approximation of, you take the convex Hall. So it's not necessarily the set of all lattice points inside the convex Hall. So you need some more arguments to show that approximatively you get every integral point in the convex Hall. So now, so I have maybe 5 minutes to talk about the arithmetic counterparts of such argument. So let me recall some notation. So L5 is some adelic line bundle. So you have En bar, which is given by pi over star of L to power n, and n phi. So you have a family of adelic vector bundles on the base adelic curve. So we need to consider the asymptotic behavior when n goes to infinity. So I just make some assumption which is not correct in general, but so with some technical efforts we can remove this assumption. So I assume that the mu mean of the tensor product of two adelic vector bundles is bounded from below by mu mean hat of E plus mu mean of F. Then what is the consequence of this assumption? The consequence is that for any t in R, if you write E point t, which is given by the direct sum of A in N, so this is a Hadana-Semon filtration that I have introduced in last talk. If you take the Hadana-Semon filtration, then it is a greater linear series of L. So the reason is that Fnt of En in some sense is given by the sum of subbundles with mu mean bounded by nt. Then if you assume this inequality, then you can check that this forms a good algebra. So that is the main technique. So with some assumptions, you have very good geometric behavior. You have some objects which is invariant by multiplication and by sum. So that is not true for lattice points on the inside the unit ball. And then this is one of the main ingredients. Also, we need the following fact for adelic vector bundle E on S. So you have the degree hat of E and degree plus hat of E minus integral of 0 to the infinity rank of Ft E dt. So this guy is bounded by 1/2 of rank E log rank E times nu of omega infinity. So in the case where E bar is Hermitian, so you just have the equality. So in general, you need to compare Hermitian adelic vector bundle to non-Hermitian adelic vector bundle. The error term is controlled here. So I will not give the detail, lacking of time, but you have already seen that in the Hermitian case, you have just the equality, so it's not hard to imagine that such inequality should be true. And then combining these two arguments, you can prove the following thing. Sorry. I will give the statement of the theorem. So assume that L is big. Then the sequence degree hat plus of En divided by n to power d plus 1 over d plus 1 factorial. So converges to d plus 1 factorial, the integral over delta of L. So this is the Newton-O'Connor body of the total graded series, and of some function which can be explicitly described. So max of some g L phi x0 dx, where g of L phi x is just a superman for any t in R, such that x belongs to delta of E point t. So E point t is given above. So just one word about the proof. So you can make a change of variable. So you see that E point t, you get fnt, so you can get some change of variable to identify this integral with rank of etn dt. So it's just a change of variable. And then you divide the two sides of n by n to power d plus 1. So you get limit of n goes to the infinity, degree plus hat of en divided by n d plus 1 over d plus 1 factorial minus d plus 1 times the integral of 0 to infinity rank of ent divided by n d over d factorial dt. So this one is converges to 0. So although here might be complicated, so I need to put every n here. So the rank of En, so it's just the big O of n to power d. And so if you divide the two sides by n to power d plus 1, and the difference here will goes to 0. And this guy converges to the volume of E point t, which is d factorial, the integral on delta of d E point t 1 dx. And then you can make some small computation, and you'll find this integral is just given by so this guy will converge to this, and then you have a double integral, so you need some change of integral, and then finally you'll find this. Okay, thank you very much.
Any question or comment?
Maybe just like a comment, not a question basically, but I found the lectures to be very motivating. So I enjoyed very much your way of explaining things, even though it's a bit difficult for me personally to follow everything. So I just want to say thank you.
Thank you very much.
And I have a comment. And is this assumption just the semi-stable conjecture for both?
Oh, I think so. It's equivalent.
Because the original statement is for the
Mu max. Yeah, but
that's just
yeah.
real.
So I need to say that anyway, I don't think this assumption be true for non-Hermitian adelic vector bundle. Anyway, in non-Hermitian case, you should not expect such thing. You always have some error term. So, but here technically, I need this thing to have a very nice algebraic condition on E point t. but with really with some technical efforts, so maybe writing 10 pages or 15 pages, so you can still have the convergence.
Yes,
So
because I think it makes sense to assume such a conjecture.
so I mean,
I
for a conjecture, for Hermitian case, you can conjecture that. So I think it's safe.
Okay.
But in general, you cannot do that.
In general, is there a counterexample?
I think so. I need to think about it, but I think so. You will have some counterexamples.
Okay. Can we generalize the classical case? I mean the case over number field. And can we
I think I mean even for a classical number field case, the conjecture would not be true if you assume a vector bundle. So if you don't restrict to Hermitian vector bundles, so that is the problem. So,
but you don't know a counterexample?
Oh, I didn't try, but I think it's not difficult.
I know for the higher dimensional rank, maybe it's dangerous.
Yeah, but
because your collaboration work with both states proves it's true for low.
But only for Hermitian one.
Okay.
Only for Hermitian one. For non-Hermitian one, I don't think that would be true. So I just didn't try to find a counterexample, but I think maybe specialized and think that it's not difficult. But so combinatorically, you need some technical computations to find a counterexample, but I don't think that would be a hard problem.
And for the problem for Openkopf body, and of course you just introduced the classical geometric setting of lattice field and Muscata. And can we generalize it? I know the classical arithmetic case, your collaboration work with Sebastian Bourson. And can we generalize it to the adelic curve case? So that is what I'm doing for the arithmetic case. That is somehow analog of my previous work with Sebastian Bourson, but in some particular case. So here, particularly for adelic curve case, yes, it's some same style generalization. Yeah. Okay, thank you.
Any more questions? Okay, thanks again.
Thank you very much.